且很强吗？不知道他这哪一版啊？他跟你说经典版，大概经典是什么时候的时期呢？我问你们，你们觉得经典版是什么时期？是 S1 吗？还是 S2？还是 S3？还是 S4？还是 S5？对不对？每个人心中的经典都是不同时期，他根本就没有一个定数，说经典版它是经典什么时期？对啊，理清都出来了。如果你觉得是 S1也是 S4，根本就没有理清，你这样网络打野已经废了，这已经不是 S2 的版本了。不要吸我经验，
哈哈哈。
来把我打死了吧？好像
First, whatever kind of model you're making, the input has to be formatted as a real number.
就对了，有感觉了，有感觉了，
It could be a two-dimensional array,
变对了。
You often think of that distinct layers, where again, each of these numbers. For example, the final layer in our processing model is a list of numbers representing the probability distribution. And this is because a key feature of these models is that the only way these parameters interact with the process is through instead of seeing the weighted sums all as various components in a matrix vector product. It's just saying the same thing if you think about how matrix vector multiplication. It's just often conceptually cleaner for you and me to think about matrices that are filled with tunable parameters. For example, those 175 billion weights in GPT-3 matrices in turn fall into 8 different categories, and what you and I are going to do is step through each one of those categories and reference the specific numbers from GPT-3 nowadays better models. This one has a certain language model to capture the world's outside of it. Specific numbers for more modern networks. I just want to set the scene going in. That as you inside a tool, almost all of the actual computation looks like matrix vector multiplication. There's a little bit of lost in the sea of billions of numbers. You should draw a very sharp distinction between the weights of the model, which are always colored blue, and the data which are always colored gray. The weights are With all of that as foundation, let's dig into the first step of this text processing example, which is to break down pieces of words or punctuation, and especially in the next one, humans think in words. This will just make it much easier to reference little examples and step. The model has a predefined some list of all possible words. Matrix has a single column for each one of these words. We label it WE, and like all the matrices, its values begin random, but they're going to be learned based on data. Turning words into common practice in machine learning long before transformers. We often call this embedding a word, which invites you to think of these vectors very deeply as points in some high-dimensional space. Of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings can be much more complicated. In GPT, and as you'll see, this coordinate space that has a lot of distinct directions. I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down on the tweaks and tunes its weights to determine how exactly words get embedded as vectors during training. It tends to settle on a set of embeddings in the space closest to that of difference between the vectors one to the tip of the other, it's very similar to the difference between king and queen. So, word for direction and searching for the embeddings closest to that point. The true embedding of queen is actually a little farther off than this would suggest, presumably because the queen used in training data is not merely a feminine version. Later relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space learned to associate some directions with Italianness and others with World War II Axis leaders. If you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, both beast and monster. One bit of mathematical intuition that's helpful to have in mind is can be thought of as a way to measure computationally. Computation has to look like weighted sums. Is positive when vectors point in similar directions, and it's negative when they point in opposite directions. For example, let's say you were playing with this model and hypothesized that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot product of It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values. So it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pair of words in our model. Specifically is 50,257. Again, technically this consists of 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we usually count up to 175 billion. You really want to think of the vectors in this embedding space as not merely representing individual about the position of that word, which we'll talk about later, but more importantly, you should think of them as having the capacity to soak in context. Specific and nuanced direction. It's a king who lived in Scotland and who had achieved his post. After murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by its surroundings, and sometimes this includes context from a long distance away. So you're putting together a model that has the ability to predict what word comes next. The goal is to somehow empower it to incorporate context. Surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to see a meaning that's much more rich and specific. The network can only process a fixed amount of each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate. Chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continue to But skipping ahead, I want to talk for a minute about what happens at the very end. Remember, the desired output is a probability distribution. For example, if the very last one is professor, in the context includes words like Harry Potter, preceding we see least favorite teacher, and also if you can pretend that tokens sound like words, then a word network that had built up knowledge of Harry Potter would probably assign a high number to the word itself. This involves two different steps. The first one is to use Then there's a function that normalizes this into a probability distribution. We'll talk more about it in just a second. But before that, it might seem a little bit weird to use this in that last step, there are thousands of other vectors in the layer. This has to do with the fact that in the training process, each one of those vectors in the final layer to simultaneously make a prediction for This matrix is called the unembedding matrix, and we give it the label WU. Again, like all the weight matrices, one for each token in the vocabulary. Then there's a function that normalizes this into a probability distribution. It's called softmax, and we'll talk more about it in just a second. But before that, it might seem a little bit weird to only use this last embedding to make a prediction. This has to do with the fact that in the training process, it turns out to be much more efficient if you simultaneously make a prediction for what will happen after it. matrix has one row for each word in the vocabulary, and each row has the same number of elements as the embedding matrix. It's very similar to the embedding matrix, just the number is swapped, so it adds another 617 million parameters to the network. More about the softmax function, since it makes another appearance for us once we dive into the attention numbers to act as a probability distribution, say a distribution over all possible numbers, and each value has to be between 0 and 1. We also need all of them to add up to 1. Matrix vector multiplication, the outputs that we get by default don't this at all. List of numbers into a valid distribution in such a way that the largest values end up in the system. That's all you really need to know. But if you're curious, the way that it works is to first raise b to the power of each of the numbers, which means you have a list of positive values, and then you can take the sum of all those positive values. You'll notice that if one of the numbers in the input is meaningfully bigger than the rest, then in the output, the corresponding term dominates the distribution. So be maximizing input. It's softer than just picking the max, in the sense that when other values are similarly large, they also give meaningful weight in the distribution, and everything changes continuously as you continuously vary the inputs. In some situations, like ChatGPT is using this distribution since it resembles the role of temperature in to the lower values, meaning the distribution is a little bit more uniform. T is smaller, bigger values will dominate more aggressively. Where in the extreme, setting T equal to 0 means I'll have GPT-3 generate a story there was A, but and then use different predictable word. And what you get ends up being kind of a trite derivative of Goldilocks. But it comes with a risk. In this case, the story starts out a bit more original, but technically speaking, the API doesn't actually let you pick a I suppose to keep their tool from doing things that are nonsensical. If you're curious the way this animation is actually working, it's taking the 20 most prominent that GPT-3 generates, which seems to be the maximum they'll give me. The probability is based on an exponent of 1/5. As another jargon, you might call the components final multiplication with the unembedding matrix, machine learning people would refer to the components in that raw, unnormalized output as the logics for the next word prediction. A lot of the this chapter is Karate Kid wax on, wax off style. You see, if you have a strong intuition for word patterns, for softmax, for how products measure similarity, and also the parameters, then understanding the attention mechanism, this cornerstone piece in the whole modern boom in AI, in the next chapter. As I'm publishing this, a draft of that next chapter is available for review by Patreon supporters. In the last chapter, you and I started to step through the internal workings of a transformer. This is one of the key pieces of technology in large language models and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need, and in this chapter, you and I will dig into what this attention mechanism is, visualizing how it processes data. As a quick recap, here's the important context I want you to have in mind. The goal of the paper that you and I are studying is to take in a piece of text. Text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. Tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional value, what we call its embedding. Now, the most important thing I want you to keep in mind is how directions in this high-dimensional space of all these tokens can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond with and a certain state in the space. You could imagine how many other directions in this high-dimensional space. The aim of a transformer is to but instead they bake in some much richer contextual meaning. Take some time for things to sink in. I think that before we dive into thinking about a couple examples of the kind of behavior that we want attention to enable. Consider the phrases American shrew mole, 1 mole of the word mole has different meanings in each one of these, based on the context. But after the first one that breaks up the text and associates each token with a vector, the vector that's associated with mole will be the same in all 3 of these cases, because it's only in the next step of the transformer that the surrounding embeddings have the chance to pass information to this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole. The attention block calculates when you need to add embedding to move it to one of these more specific associated with lots of other wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally, than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially one that's far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how after all embeddings flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next vector is entirely a function of the last vector in the sequence. That the testy input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model is going to accurately predict the next word, that final vector will have to have been updated by all of the attention blocks to represent much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computation the verdant forest. For the moment, suppose that the only type of update that we can have is having the adjectives just nouns. What I'm about to describe is what we would call a single attention, and later we will see how the consists of many different heads run in parallel. Again, the initial encoding for each word is only includes the meaning of that particular word with no context. Actually, that's not quite right. We also encode the position of the word. to have a series of computations produce a new refined set of embeddings where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are tunable bits, things that we learn based on data. To be clear, I am not behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to trace because it's based on some cost function. It's just that as we step through all of the different matrices for the parameters that are involved of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each feature, like creature, asking the question, are there any adjectives in the and for the words fluffy, and I'm in that position. Another list of numbers, which we call the query for this word. This query has a much simpler function than the embedding. Say, looks like taking a certain matrix, which I will go into, and multiplying it by the embedding. Pressing let's write that query vector as Q, and then a matrix next to an embeddings in the context, producing one query vector for each token. The entries of this matrix are in practice, what this matrix does in a particular attention head is imagining an example that we might hope that it would learn. Smaller query space includes the notion of looking for adjectives in preceding positions. Who knows? Maybe it simultaneously tries to accomplish some other goals. Right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix, which is also multiplied by every one of the embeddings. This produces a second series of keys. Conceptually, you want to think of the keys as potentially answering the queries. Just like query matrix to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other. Match the adjectives, like fluffy and blue, that more closely align with the query produced by the word creature. To measure how well each key matches the query, you can use a dot product between each possible key and head. I like to visualize a word full of a bunch of dots, and the bigger dots point to the this is where the keys and queries align. Fluffy and blue. The dot products in these
Oh, what is the end now?
some large positive numbers. Say that this means the embeddings of fluffy and blue attend to the embedding of creature. In contrast to the dot product between the key for some other word, like the, and the queries for creature, would be some so we have this that can be giving us a score for how relevant each word is to updating the meaning of that particular word. The way we're about to use these scores is to take a so instead of having values range from negative infinity to infinity, what we want is for the numbers in these
完了，听不懂，完了，完了，来看看啊，休息，哦，头痛。 key embedded. Carry key. This carry vector is the order cancel key vector. Computes the row alignment to every query keys in the key. Normalize this code. Okay, maybe upload.
Columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. Compute a softmax along each one of these columns to normalize the values. All of the columns will fill in the grid with these normalized values. We call this grid an attention paper. There's a really compact way that they write this all down. Here, the variables q and k represent the probabilities of query and key values, respectively. You get by multiplying the query and key matrices. This expression up in the numerator is a really compact way to represent the keys and queries. Query space. Then this softmax that's wrapped around the whole expression is As to that V term, we'll talk about it in just a second. Before that, during the training process, when you run this model on a text example, and all of it based on how high a probability is, if you simultaneously predict every possible next token following each initial it might also be predicting what words follow creature and what words follow effectively acts as many. For the purposes of our attention, it means that you never have to for what comes next. What this means
way.
The simplest thing you might think of is that the columns wouldn't add up to 1 anymore. They wouldn't be normalized. So instead, the way to do this is that before you set those entries to then after softmax, all of those get turned to 0, but the columns stay normalized. This process is called masking. There are versions of where you apply it, but in reflecting on about this attention pattern is how its size is equal to the square of the context size. So this is why context size can be a really huge bottleneck for large language models, and scaling it up is desire for bigger and bigger context windows. Lets the model allowing words to pass information to whichever creature that moves it to a different part of this 12,000 encodes a fluffy creature. What I'm going to do here is first show you the most straightforward way that you could do this. This most straightforward way would be to use a third matrix, what we call the value matrix, which you multiply by the embedding of that first word, for example, fluffy. The result of this is what you would call a value vector. This is something that you add to the embedding of the second word. In this case, something you add to the embedding of fluffy. So this value vector lives in the same three-dimensional space as the embeddings. When you multiply this value matrix by the embedding of a word, looking back in our diagram, let's set aside all of the keys and the queries, since after you complete the attention pattern, you're done with those. Then you're going to take this value matrix and multiply it by every one of those embeddings. You might think of these value vectors as being kind of associated with each column in this diagram. You multiply each of the value vectors by the corresponding weight in that column. For example, here, under the embedding fluffy, or at least nearly zero that. And then finally, the way to actually update the embedding associated with this column. You add together all of these rescaled values in the column, producing a change that you want to add that to the original embedding. Hopefully, what results is a value vector encoding a more contextual. You don't just do this to one embedding. You apply the same weighted sum across all of the columns in this picture, the corresponding embeddings produces a full sequence of more refined embeddings popping out of the attention block. Of attention. As I described so far, this process is parameterized by three distinct matrices, the query, and the value. I want to take a moment to continue what we started in the last chapter, with scorekeeping, where we count the model parameters using the numbers from the query space. This gives us an additional 1.5 million or so parameters for each one. If you look at that value matrix by contrast, it's a square matrix that has 12,288 columns and 12,288 rows, since its inputs and its outputs serve as a large embedding space. If we that would mean about 150 million added parameters. And to than to the key and query. Parameters devoted to this value map is the same as the number devoted to the key in the query. This is especially the way this looks is that the value map is factored as a two small matrices. Think about the overall linear map. One inputs and outputs in this larger embedding space. For example, taking two separate steps. The first one has a smaller number of rows, typically the same size as the previous space, but these, as you can think of it, as manually large vectors down to a smaller space. This is not conventional, about it in my opinion, it tends to make things conceptually constraining the overall value map to be a low-range transformation. Going back to the parameter count, all four of these matrices have the same size, and adding them all up, we get about 6.3 million parameters. As a quick side note, to be a little more accurate, everything described so far is what people would call a self-attention head. reciprocity. This isn't really types of data, like text in one language and text in another language that's part of an audio input of speech and an ongoing transcription. A concept looks almost identical. The only difference is on different data sets. In a model doing translation, for example, correspond to which words in another. Since there's not if you understood everything if you were to stop here, you can away with the what attention really is. What's really left to us is to lay out the sense of many different times. In our simple example, we focused on updating nouns, but of course, for the shape and the structure of that car. And a lot of associations might be less grammatical. If the word wizard instead the words Queen, Sussex, and William were in that passage, the Harry should instead be updated to refer to the prince. Imagine the parameters of these key include matrices will be used to capture the different attention patterns, and the parameters of our value map. In practice, the true behavior of these maps is much more difficult. The weights are set to do as I said before, everything we described is a single attention, and the full attention multi-head, where you run a lot of these operations in parallel. GPT-3, for example, uses 96 attention heads inside each block. Just to spell it all out very explicitly, this means producing 96 distinct attention patterns. Then each head has its own distinct value matrices used to produce 96 sequences of value vectors. These are all added together using corresponding attention patterns as weights. What this means is that for each position in the context, each token, every one of these heads produces a change to be added to the This entire sum here will be one slice of what's outputted from this multi-headed attention block. A single one of those defined This is a lot to think about, so don't worry at all if it takes some time to settle. Giving the model ways that context changes meaning. Ends up with around 600 million parameters. There's one added slightly transformers. You remember how I said that the value map is factored out into these two distinct matrices, labeled as the value down and the value up matrices. The way that things would suggest that you see this but the way that you see this written in value up matrices for each one appear stapled together in one giant matrix, the entire multi-headed attention head. And you can see for a given attention head, they're typically only referring to this first step, the one that I was labeling as the value down projection into the smaller space. I've left a note about it. It's one of those details that makes the risk of distracting conceptual ideas, but I do want to call it out just so that you know if you read about it. It doesn't just flow through a single block. For one thing, it also goes through these other operations this more nuanced embedding influenced by its more nuanced surroundings. The further down the network you go, with each embedding taking there's the capacity to encode higher level and more abstract ideas about a given input beyond just discourse and and relevant to the piece, things like so the total number of key, query, and value parameters is multiplied by another 96, which brings the total sum to just under 58 billion distinct parameters devoted to all of the attention heads. It's a lot, to be sure, but it's only about a third of the 175 billion. So even though attention gets all of the attention, the majority of parameters is not so much any specific kind of behavior,
Ole.
it's extremely parallelizable, meaning that you can run
不行了，不行了，不行了。
using GPUs. Given
疯
that
掉了。
the big lesson of the last decade or two has been that scale alone seems to give huge
休息一下啊，休息一下，休息一下。哦，天，今天哦。啊。看个废片哦。废片时间。看过了，新的。
You ready? So we're gonna be starting with Breaking Bad. Say my name. I am so freaking excited.
有哎，好了。
What the heck is this? We got the agreement, right? I got my 10. What the
钱啦。
You know what? That's it. I'm not saying this line. I'm gay. I'm gonna say it. I'm gay, and I want you to know, Mike, my butt. I want it. I want to be the kid named Finger. Just do it now, right? Come on. Why would we want you in the? What's my line? What? Wait, what is this? This is gonna be so bad. Okay, so we just wish you right here, right now. Leave you in the desert, and there is no more Coke on the market. What Coca-Cola? Alright. So, if we just wish you right. Frank, you go first. You go first. It's so hard! It's so long! It's 7 of 41! 41 flips! This is a jerky little. You know, that's what they say. I'm just making my wrist look. Oh, okay. That's what you say. I'm just wondering why we're so lucky. What could have said me? I messed up my line! We don't have time. We gotta keep going. Am I Walter White? Is this Walter White?
Yes.
The man who's keeping it.
I'm the man who's keeping it. I thought something like her. What the? I'm the man who's keeping it. Wait, we could make him sound like he's really drunk.
到底有没有
Just
算？
that sounded like his song.
1,000 gallons of methylamine is worth more in my hands than anyone else.
Oh my god, he's yapping so much. 1,000 gallons of cum.
越打钱越少。
Or anyone else's. But I need
什么游戏？
Now, you have the opportunity to sell it yourself.
But now, you have the opportunity to suck my balls. Oh my god, it's happening! Everyone watch! Wait, my score is... My score is that bad? You ready? Who the heck are you? I'm the man who's keeping it. What's this? We had an agreement, right? We had our deal, so where's the tape, Mike? Mike doesn't know what it is. I'm dealing with me now, not him. Let's just cut what it is you want or what you think is gonna happen here, alright? Cause we're gonna get what we came for. $1,000 is worth more in my hands than yours or anyone else's. But I need distribution. Distribution? That's right.
Distribution.
So if you agree to give, you'll cook. And so mine come instead. I'll give you 35% of the tape. You know what? That's it. I'm not saying this line. I'm gay. I'm gonna say it. I'm gay, and I want you to know. Mike, finger my butt. I want it. I want to be the kid named Finger. Just do it now. Right? Come on. Why would we want you in the... What's my line? I know all about your nipples. See, my nipples are small, and your nipples are big and ready to be milked, and I want them. I should give them to me. Also, I'm the one who knocks.
Say my name.
So, it's grade school team versus the New York Yankees. Yours is just some tepid off-brand generic tells me that you switched to a P2P cook because you dye your cum to make it look like mine. You already ate my cum in every tea. But now, you have the opportunity to suck my balls. I need you to listen to me. We're not gonna give up this.
Penis.
We have 40 pounds of cum. Ready to go. Are you ready?
Same. Yo. Yeah.
Oh my god, cinema! Touch me. Oh, wait, no, not touching. They're not touching. Look, whatever you show me. And just so you know, my brother-in-law is a gay porn
So good.
If they ever do
100%.
they need to hire me. I actually want to voice act her, and I won't. What was I thinking? Please.
Who are you talking to right now?
We did it in the other clip.
A business. Big enough that it could be listed on the map.
Penis.
Disappears. Danger, Skylar. I am the danger.
I am the danger.
I am not danger, Skylar. A guy opens his door and gets shot, and you think that of me? No. A guy opens his door and gets shot, and you think that of me? No.
Locks. Badass. Locks. Whoa, 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 whoa.
Minding my own business.
So do I.
Oh my god, that's long.
Every man, woman, and child in this country.
Woman and child. Are you freaking kidding me?
I believe that until proven guilty, every man.
I believe that until proven guilty, every man, woman, and child in this country is innocent. That's why I jerked for you, Albuquerque! Touch my balls? That really? Touch my balls? Oh my god, this is the best I've ever done. Are you ready to see this? I had a good job until my boss accused me of a jerk. I better call him Sam. You are under and so do I. I believe that until proven guilty, every man, woman, and child in this country is innocent. And that's why I jerked for you, Albuquerque. I guess we're digging a hole. What? It's gonna take forever!
Elefante. Elephant.
What's that? What is that? I got a rock! Can I sell my rock? No, I mean rocks! My batteries low? What, my rose toy? Oh my god, this is so pretty. Made a poll. Lock in. I'm gonna do
Alla fonte.
What is that? I'm adding lumps to my
不得不说，基努里维长得真的很像耶稣。 不行了，修了。